Hi guys, welcome to GTN Abacus Learning.
In the last session, we solved a problem related to springs in series, this one here, and we compared the results with the abacus analysis and found out that the reactions and the displacements were the same. There is also an easier method to obtain the global matrix directly by looking at your system from the first principle of the definition of the stiffness. By stiffness, we mean force required to displace a node in a certain direction by a unit displacement, in this case a unit millimeter, while the other degrees of freedoms are fixed or restrained. For example, if we take the same problem and we try to determine the global matrix of this one directly, then we redraw the springs. We are concerned about the displacement in this direction, direction 1. We form a 4 by 4 matrix because there are 4 degrees of freedom altogether, so it will form a 4 by 4 matrix. We can form a matrix which is a 4 by 4, and we can name the first column as 1, second column as 2, third column as 3, 4, here also 1, 2, 3 and 4. Now, according to the basic principle of stiffness, if we focus on finding the values of the first row, which means that when we displace this point, this node in this direction by a unit, we have to find the forces at each of the nodes and fill them correspondingly while these are fixed. In this case, if we fix this, and this, and we displace this by unit 1, then according to the stiffness of this spring here, which is 1 kilonewton, then it will require a 1 kilonewton force to displace it by 1 millimeter. So we have a 1 kilonewton force acting in this direction. This is node 3, where a reaction will be produced in the opposite direction, which also equals to 1. Now, since this is node 3, we put the value at node 3 here in opposite direction. Since the force won't transfer to node 4 and 2, then you'll have 0 reaction here and 0 reaction here. That's your first row. Now, if you want to find the values of your second row, it means that we have to find the reactions at each of the nodes while displacing node 2 by 1 millimeter. In this case, I have to fix this and this, and then displace this by 1 millimeter. The force required would be 3 kilonewton. So we write 3 kilonewton here. So the force required here will be 3 kilonewton. And the reaction will be produced at node 4 in the opposite direction to balance this force. And since the displacement won't transfer to these nodes, their values will be 0. So we put 0 here for 1, 0 here for 3, but for 4 we get minus 3. Similarly, when we focus on the third node, we displace this by 1 millimeters and then find reaction forces at all of these. If we displace this point by 1 millimeter, the force we get would be 2 plus 1 because we are pushing on this spring and pulling on this spring By pushing, I mean this spring is going to contract and this is going to expand. I will require 2 kilonewton force to compress this one, and then a 1 kilonewton force to pull this one, which equals to 3 kilonewtons. So for this one we put 3 here. Now if you want the reactions, there will be two reactions here, reaction at node 1 and reaction at node 4. Here, since it requires 1 kilonewton force to move this or to stretch this by 1 millimeter, we have 1 kilonewton here, and similarly we'll have 2 kilonewton force here. Therefore we write 1 here, negative, and at 4 we write minus 2, and here it will be 0 because displacement doesn't transfer to this spring. Now if we focus on the fourth node, we fix 1, 3 and 2, and then move this node by 1 millimeter. We require 2 plus 3, that's 5 kilonewton force, and we'll get reaction of 2 kilonewton here and reaction of 3 kilonewton here. We put 5 here, and at node 4, at node 1 it will be 0, at node 3 it will be minus 2, and at node 2 it will be minus 3. Now let's compare this global matrix with the one we previously obtained. We'll find that the values are all the same. So this is how you obtain your stiffness matrix by the first principle. In addition to this problem, you can try something like this, and then let's say this is K, where K equals to 2 kilonewton per millimeter. In this problem, rather than force, you can apply a certain displacement at this node, let's say 20 millimeters, and then obtain your forces and displacements at these nodes. So you can try this by hand calculation and then model this in ABAQUS and see how this spring behaves. Now let's move into today's problem. What we'll try to solve today will be something like this, where we'll have three different elements. That's element number 1, element number 2, and element number 3, which is an assembly of rods. Let us say that this is 30 inches, and let us say that we have a force acting at this point here, which equals to P, and let that P be 3000 pounds. We'll now label our nodes. Let us say that the Young's modulus for element 1 and element 2 are equal, and they are equal to 30 into 10 to the power 6 psi, and the areas of A1 and A2 be the same as 1 inch square. But for the third element, let us say that E3 is half of this, 15 into 10 to the power 6 psi, and area be twice of this, 2 inches square. The problem here is to find out what are the displacements in the actual direction at node 2 and node 3 and to find the reaction forces at node 1 and node 4. For this, we can just follow our general procedure. We write our stiffness matrices for element 1 and 2, which will be equal to, and K3 will be equal to, we can then substitute our values and put them here, and then form the global matrix. Then we'll have our force vector, which will be equal to K matrix into displacement vector. I'll use this symbol for vectors and this symbol for matrices. Then if we put in the boundary conditions like we did in our previous problem, then you'll obtain your displacements at u2 and u3 in the x direction and your reaction forces would be. Now let us model this in ABAQUS and see what we get. For this, it will be slightly different than the spring system that we did last time because we have to individually form our parts here. So let's get it started. Please make sure that you have this option available. Let's make our parts. As we see in our problem that we have 3 rods, but 2 of the rods have the same properties and the third one has different properties. So let's make steel rod 1 and 2 as a single part. You click on 2D, deformable and wire, and just keep the size at 200. So let's make the wire section, which is of 30 inches. And let's make another part, steel rod 3, similarly 2D deformable wire, and continue. Make this one as 30 as well. So these are our parts, steel rod 1, 2 and steel rod 3. Now let's go to materials. In this section we describe various materials so we can assign them individually to our parts. So let's make this section steel 1. In this problem we only have the elastic modulus, so we go to mechanical elasticity and click on elastic. There you can assign your modulus of elasticity as 30 E6 and Poisson's ratio just keep it as 0.26 and click OK. So this is steel 1 and 2. So assign a different material. For our steel rod 3, go to mechanical elasticity elastic and then assign 15 E6. There you have your two materials. For these wire section, because since we are dealing with 2D, we have to form some profiles that will define our cross-sectional shape and area. So here we are only given area, not the cross-sectional geometry. Therefore, we can just select on rectangular, just make it profile 1 and 2. So you can assign it to steel rod 1 and 2. Go to rectangular, continue, and here you can put the dimensions. So for rod 1 and 2 we are given 1 inch square, so you can just put 1 here and 1 here, so the area becomes 1 inch square. And again we make another profile which is a rectangular profile as well. This is for rod 3, so we name it profile 3 and click on rectangular and continue, and we are given that it is 2 inch square, so you can just put 1 here and 2 here, so the area becomes 2 inch square. Click on OK. And then we also have to make different sections, so we name it section 1 and 2, so you can assign this to our steel rod 1 and 2. Click on beam and then beam. So here you have to assign your profile name, so that's profile 1 2, your material name steel 1 2, and your Poisson's ratio which is 0.26, and click on OK. And you define our another section, section 3. Click on beam That's our profile 3, steel 3, Poisson's ratio the same, 0.26. Okay, now we go back to our parts, steel rod 1, go to section assignment, make sure you select all of it, click done, and you select your section 1 and 2. Now we have to assign our beam orientation, which defines the directions of its local axis. So you go to assign, since this is a beam, go to beam section orientation, make sure you select all of it, click done, and then click enter. Okay, that's it. You can also click on orientations. So this is for the local material orientation. Select all of it, click done, use default, just click on OK. That's for steel rod 1 and 2, and then you go to the next one, do the same. Now we have created our parts, assigned the material properties, and assigned their cross-sectional properties. Now what we want to do is we want to mesh them. Meshing is a very important section in your modeling, because the type of meshing, the degree of meshing determines how accurate is your solution. It also determines how fast is your analysis is going to run. Therefore, many people do mesh analysis before going into the deeper analysis of the section. So for meshing this rod, you go to seed. Seed means you can assign how big, how large your mesh is going to be. If you write 3 here, it will mean this beam section will be divided into 3 inches, so there will be 10 finite elements. So let us put this one as 1, so we make 30 individual elements. So click apply, so you'll see that these are 30. So click OK, and then go to mesh, go to part, and then click yes. Now it has been meshed. We can go to steel rod 1 and 2 and then do the same. That's it. So we are done with the part now. We are done with the meshing. Now let's go to assembly. Assembly is a section, is a space where you can assemble your different parts in many ways. So for this one, we are just assembling our parts in linear fashion. Let's take this part out. This is your rod 1, 2. So click apply. It will be easier if you translate one end of the beam to the center of your space. So for this, you click on translate and then click on the section you want to move, hit enter, and then click on the point you want to move and click on the point where you want it to be. So click OK, and then you have your first beam. Now since our second beam is similar to this one, what we can do is that we can create a linear pattern. Linear pattern means like array in AutoCAD, where you can replicate your parts. This is your X direction for now. This is your Y direction. You can change your direction by clicking here. You can select your other direction as well. Let this be 1. We don't want to replicate in the Y direction. Let it be 35 for now. Okay, so you have your steel rod 1, steel rod 2, and we also have to put steel rod 3. So we take steel rod 3, click OK, and then you can translate this part, this beam, to the end of your second rod, and you can translate this one to translate this 0 by 5 inches to your right. So 5 inches to your right. So there you go. The reason I'm separating these rods is that we have to assign a connector properties between these two. If we put this rod right next to, or right at the end of this rod, Abacus won't recognize that it is connected. You have to specify that it is connected in some ways. So there are various methods of connecting different elements depending upon your requirement. So let's just bring this back to our position. Now to connect this, we have to form some connector sections. So we go to connector sections, just go to beam. By beam we mean that whatever happens in this node will also happen in this node as well. So these two nodes are kind of tied, and similarly for these two nodes as well. So click on beam, and then you can see your diagram, your connection type here. Or let's say we have hinge. If you click hinge, now that's your hinge. This is your connection, which means that if we assign your hinge here, this part can rotate up and down at this node. So let's use beam here, and then click continue. So that's your beam. Click OK. And then to assign your connectors, you have to create your feature wires. You click here and then click add, so you can form the wire features between these 2 points and these 2 points. Click done, and then click OK. Now here you have to assign your connectors, what type of connections they are. For this you go to assembly and then connector assignments. So you select our wires, click done, and it will assign that as your section that you created here, or you can create new sections here, new connections. So orientation 1 and 2 will be automatically defined, so click OK. Now Abacus knows that these are connected. Now we're done with the assignment as well. Now let's go to step. So this is also static. Click on static journal 1 increment. You want to increase that. Then go to field output request. For this we only require displacements and reactions, but let it be default. It's alright. Make sure that you have put 1 here. Click on amplitudes and force, which is 0 at 0. At 1 second it will be 3000 pounds. Now go to loads. You create your load here, create concentrated force, and you can set your load here. Click done, and that's click 1 here, forces, and in the y direction 0. So that's your force acting here, 3000 pounds. And we create our boundary conditions now. For the fixed boundary condition, you can just click here. You can select out 2 ends where they are fixed and click done. And you can just incastrate them. That's it. So you have your model ready. You can save your model and let's run it. Let's create our job. This is rods in series. Then click on submit. So click dismiss and let's see our results. Now this is our system. Let's look at our displacements. Click here and you can play it. So this is moving. So you can see here that this is being stretched. This is scaled by a factor of 5000, and you can actually see the direction of your displacements. And you can click here and then change the density of your arrows, so you can decrease the density. I'll just keep it at this one. You can observe that the highest, let's go to the end here, the highest displacement is around 0.002, which occurs here at this node. And if we look at our solution, we do have the same value here. And let's look at our forces. You can click on reaction forces, RF. You can see the arrows here. Now let's just change the density to high because we only have 2 points where the reaction forces will occur. Click here, click high, apply. So you can see the reaction forces occurring at these 2 points, and you can just play it. Now if you want to see the values, you click here, symbol options, and then click your labels, and you can say display the value next to the vector symbol. So click apply and then OK. Now you can see your forces. If you look at the end, we'll see that this is 2000, this is 1000, both acting in the same direction. If we check our solution, we also obtain 2000 and 1000 pounds. As I discussed before, in my previous video as well, we can get the data from this response. You just click on variables and then go to unique nodal. Let's plot our reaction forces and select the node you want to plot your forces. Click here and then you can just plot it. That's your force in the y direction. That's your force in the x direction, and that's your resultant. You can see here, this is the vector sum of this and this. You get the resultant, which is plotted in positive direction. So we know that it goes to 2000 pounds. Let's plot the different node. Click here and then edit. You can click on this one, click plot. So that's your vertical reaction, which is 0, and this is your horizontal reaction, and that's the vector sum of this and this. That's the resultant, which goes up to 1000 pounds. Also, you can plot our displacements. You can just click on U1 because that's the one we want to see, and then elements. You can edit, and let's plot this part here. Click done. Click on plot, and you'll see that it goes up to 0.002 inches, and you can plot the other one as well. You can add a different node here as well. So you can just click on this one and click add. You can select both of them and plot. You'll see that there's one which goes up to 0.002 inches, and we have the other one that goes up to 0.001. Alright, so today we learned how to model line elements and how to assign certain connections between the two elements. Thank you for watching till the end. Please comment, share and subscribe to this channel. Thank you.